Hey, welcome! Have you ever looked at one of those giant MRI machines and just wondered how on earth does that thing see inside our bodies with such insane detail, all without using a single X-ray? Well, today we're going to pull back the curtain on magnetic resonance imaging, or MRI. And I promise, by the end of this, the beautiful science behind it is not only going to make sense, it's going to seem almost like magic. So, let's jump right in.
So, this is it. This is the big question. How can we possibly take something like a magnet and some radio waves, things we have all around us, and use them to create these stunningly complex pictures of the human brain, or muscles, or organs? Well, the answer is kind of mind-blowing, because the most important piece of equipment in the whole process is actually you.
That's right. The absolute first thing you have to understand about MRI is that our bodies, your body, is filled with literally billions and billions of microscopic magnets. No, this isn't some sci-fi movie plot. It's just a basic property of what we're all made of. So why hydrogen? I mean, of all the elements, why that one? It's simple, really. Our bodies are mostly water, something like 60% water. And of course, every single water molecule has 2 hydrogen atoms in it, so we are just packed to the brim with them. This makes hydrogen the perfect, most abundant target for the MRI machine to find. Okay, so here's where it gets really cool. Every single one of those hydrogen nuclei has 1 proton. That proton has a positive charge, and it's not just sitting there, it's constantly spinning. Now, a little rule from physics for you. A spinning charge creates its own magnetic field. So right now, as you're sitting there, you have countless tiny hydrogen atoms, and every single one is acting like a teeny tiny magnet, all pointing in completely random directions. All right, so inside our bodies, we've got this huge orchestra of tiny little magnets, but right now, it's total chaos. They're all doing their own thing. So how does an MRI machine get them all to play in harmony? Well, this is where we tune the instrument. We need to get all those protons to basically face the same way.
The moment you slide into that MRI tube, you're entering an incredibly powerful magnetic field. We call it B0. And get this, it's always on. This massive field forces the vast majority of those little hydrogen magnets to stop pointing every which way and snap into alignment with it. But they don't just sit perfectly still. They start to wobble around that main magnetic field, a motion we call precession.
This is the perfect way to picture it. You've seen a spinning top, right? It's spinning super fast on its own axis, but as it starts to slow down a little, it also starts to make that slow, wide wobble. That wobble, that is exactly what precession is. Our hydrogen nuclei are doing the very same thing inside that magnetic field, and they're all wobbling at a very specific, predictable speed. Okay, so our instrument is officially tuned. All our little magnets are lined up and wobbling together at the same frequency. The next step? We need to actually get a signal out of them. And to do that, we have to, well, pluck the strings.
This is a really important difference to get. That B0 field is the huge, always-on magnet that does the tuning. But then, for a very brief moment, the machine sends in a second, much smaller magnetic field. It's a pulse of radio frequency energy, and we call it B1. This isn't a static field. It's a quick burst of energy that acts like a pluck, and it literally knocks the spinning magnets sideways out of their alignment. And here is the absolute magic of it all. For that pluck to actually work, the radio frequency pulse has to be tuned to the exact same frequency as the wobbling protons. It's like an opera singer hitting just the right note to shatter a wine glass. When the frequencies match perfectly, you get the most efficient energy transfer. That perfect match is called resonance. It's the R in MRI.
Now you might be thinking, hold on a second. If all the magnets are already lined up with the main field, why can't we just measure them then? Why go through this whole complicated flipping process? And you know what? That's a fantastic question. And there are 2 really critical reasons. First, that main B0 magnet is so unbelievably strong, trying to pick up the tiny little signal from the hydrogen nuclei inside of it would be like trying to hear a whisper during a jet engine takeoff. It's completely drowned out. And second, the physics of it just works out this way. The machine's antennas can only pick up an electrical signal when those magnets have been knocked sideways and are spinning around in that new plane. So yeah, that flip is absolutely essential.
Okay, so we've tuned the protons with the big magnet, and we've plucked them with that radio pulse. What's next? We listen. The machine turns off the radio pulse, and immediately the protons start to relax and go back to where they were before. And as they do, they give back the energy they absorbed. The MRI machine is basically just a super sensitive antenna, listening for this incredibly faint echo coming from our own body.
And it turns out it's not just one echo.
The machine is actually listening for two different kinds of signals. The first is called T1. That's all about how quickly the protons snap back into alignment with the main magnet. The second is called T2. That's about how quickly the protons, which were all spinning perfectly together, start to fall out of sync with each other. It's kind of like the difference between how fast a guitar string stops moving up and down versus how long the sound actually hangs in the air.
Now for the grand finale. This is the most incredible part. We've got all these faint signals, these little echoes coming from all over the body. Now all we have to do is turn that music into a picture.
And here is the secret sauce. The hydrogen protons that are in your body's fat relax and give off their T1 and T2 signals at a totally different speed than the protons in your muscle, or in your brain tissue, or just in water. Every single type of tissue has its own unique signal signature.
So really, you can think of it like this. Different parts of your body are all singing a slightly different song. The MRI machine listens to all of these unique songs and knows exactly where they're coming from. Then the computer just builds a map of that music. It assigns a shade of gray based on how loud and what kind of song it hears, and suddenly you have a detailed image composed entirely from the music of your atoms. It's just amazing.
So what you're seeing in an MRI, it isn't really a picture like a camera takes. It's a map. It's a map of the hydrogen in your body and how it behaves differently depending on the tissue it's in. It's an incredible story of physics and biology all working together. And that kind of leaves us with a final, fascinating question. Today, we listen to hydrogen. What other atoms are in there, just waiting for us to figure out how to listen to their song?